intersections or self-intersections. Yeah, so it is a way to prove it, and I will use it today to show you I will use it today to prove the general theorem. And also we can do it also I can do it in reverse using another theorem that also was already proved recently. So there is a necessary condition such that it gives the existence, or I should better say there is a condition that provides that there are no points of intersections or self-intersection of n independent processes. So these two results will be the basis of what I'm doing right now. And as you can see in the last result, I have Brownian motion in Carnot group, and this is the reason I will consider Brownian motion in Carnot group. Yeah, I have to note that, of course, the approach by the Fitzsimmons-Salisbury multi-parameter Markov process, it is much more general and theoretically should also provide results in this case also. But for me, there are some complications there, so I cannot right away tell you that I have some condition from the work. So, right now, I will just use my own results. So what is Brownian motion Carnot group? I will not give you full definition, just a bit of reminder that in fact this is just a solution of some kind of equation, stochastic differential equation with Stratonovich integral, because we, of course, Carnot group is a Lie group, which is a manifold, so it is convenient to use Stratonovich integration. And these vector fields, well, they have a very, they can be defined exactly as such vector fields that have some coordinates at 0 equal to 1, and the rest is 0. So they have very special definition. I just don't want to give too much details. It is important to know that these vector fields have polynomial coefficients, and they are in fact allows for this equation to be solved just by direct integration. So, for example, first coordinate of this equation does not depend on any other. The second coordinate does not depend on any below, only maybe on x1 and so on. So this triangular system can be just integrated. And example of such system and such process, you can see the first several coordinates are just Brownian motions, they just integrated, right? And then the third coordinate, if we integrate, we obtain such object, which is Levy area. Yeah, so this is typical process of such kind. Of course, it seems that it's just some very special kind of process, but in fact, it is known that if we consider such processes, then we can use them to approximate any diffusion in the neighborhood of a point. It is, of course, a little bit problematic from my point of view, because I do not know how this approximation applies to the theory of intersection, self-intersection. But at the moment, I think it is interesting to consider this type of process, because they already reach enough to give us an interesting result. Okay. So yeah, so now I will have to define so-called non-singular points. So I call point non-singular on this H. H was the set of points such that this is the points where the process, the function of the processes may intersect. So, for example, if n equal 2 and OF are just x, yes, so what we have is just we have the diagonal, right? So we have H is just x1 equal x2. it may be multidimensional, but it is just multidimensional diagonals. It is just diagonal. So on this diagonal, I cannot prove everything for every point. So I will use such definition of non-singular point. This is such point at which any family of such vectors where Vs are just some kind of Lig, where Lig is again left invariant vector fields that correspond to the group Ji. Yes, so we have group Ji, and on this group, before I only used K vector fields. This was just so-called first slice of the corresponding Lie algebra, which means that all other vector fields can be obtained as a linear combination of commutators of this first Ki vector fields. But then we can also define corresponding degrees of this vector field. So if the vector fields are in first slice, they have degree 1. So here we have P equal to 1, corresponding P, yes, corresponding degree to here is 1. And if we look at the commutators of this, then P will be equal to 2. And if we take commutators of those again with this, then P will be equal to 3, and so on. So this is just degree here is kind of number of nested commutators you need to take to get this +1. So it is my setup, and this Lig is used here. They are used here, but they acting not on Ge, but on G1, on Descartes product, but they act on the corresponding coordinate. So Leg act on coordinate E, so act on group G. So it is how this V vector fields V defined. So, and if we consider such family of vectors, then I claim that the point is non-singular if they are either linearly dependent or linearly independent in some small neighborhood of X and intersect with this H. So let me draw a picture. So for example, if H some kind of manifold like this, so what can happen if we have V1 like this at this point, but then at this point it becomes parallel to this H, right? So the point at which V1 becomes parallel is singular point, so we cannot include it in our consideration. This is the idea here, and of course, the general condition is that if I take any number of vector fields, right, and then I project them onto the orthogonal space to the tangent space, then this dimension of such projection has to stay constant in some neighborhood of X when we are on the surface. Okay, so this is my singular and non-singular points. And the important statement is that in fact such points are open set. All such points is an open set in H. So it is open in the sense that for any such point, some small neighborhood intersecting with H also with such point. So non-singular points, it's obvious, right? So, but it is an open set, but also it's H minus this U0 is nowhere dense. So the complement of this set, the set of all singular points, is nowhere dense. So this means that the set is in some sense small. Unfortunately, I cannot say that this set has measure 0, surface measure 0 something, and the reason is because, as you can see, this is related to this condition. Yeah, so we have some GSX is some determinant which is infinitely differential function. So if we write GS equal to 0. So generally speaking, it is also a manifold. So we have intersection of two manifolds. And when we have intersection of two manifolds, then we can have problems. This intersection of two manifolds can be quite complicated. So what I call non-singular points is exactly the points where this does not happen. So this is what I need to proceed. Yeah, and of course, the fact that it's nowhere dense is basically obvious from the definition. So, and now the main result. So what if I only consider non-singular points? And turns out that in case m equal 1 or m equal 2, n equal 2, we have that probabilities that no trajectories visit set to 0 is positive. Which is understandable, because if we have one-dimensional processes, what is M? I recall that M is a dimension of the set of the images of trajectories. Yeah, so the dimension of the images is exactly M. So basically, if M equals to 1, we look at the intersection of one-dimensional process. Obviously, it should exist. Yeah, this positive probability. And if M equal to 2, n equal to 2, then we look at the intersection of two-dimensional processes. And this is also, it's actually easy to understand why this is true without any additional proof, but I will also give you a proof. But suppose that we have two-dimensional processes that and in fact, we know that these processes we can control. So we can say that they at some point of time, this process belongs to some ball with positive probability. Yeah, and we can then make a tube and say that this process is in this tube. Starting from some time, ending some time. And it also have positive probability. And then we can claim that at some other point of time, it arrives from here to here. Yeah, so it's in some other ball. So we can control the process. And then we can control the other process so that they actually intersect. Yeah. So in two dimension, it is clear that two processes have to intersect. If they, of course, if we control them like that. But Brownian motions, Carnot group, they are similar to usual Brownian motion in the sense that they can also be controlled in this way. So this theorem is actually more or less understandable, but this one is already, I do not know how to do it except the method that I'm going to tell you today. So and here I will here u0 is not needed, of course, but here it is important that I use u0. So if the dimension of the process is greater than equal 4, or dimension of the process is 3, and then there are at least 3 different independent processes, then the probability that the images intersect, yes, so these images intersect is 0. But only if I restrict the intersection to the set u0. So, and this is a definition that is needed for the next case. So you see that I already considered 1, 2, 3, and 4, except in the dimension 2, I need also to consider n greater than equals than 3. And if I consider n greater than equals than 3, then I arrive to the following condition. So it turns out this is the condition which is necessary and sufficient for such probability to be 0. Not 0, not 0. Вибачте, sorry, yeah. So you see QE here is exactly this by this definition. So this is so-called I don't know if it's okay to call it like that, but it may be called some kind of homogeneous codimension of this manifold. So here we look at the set of vector fields such that the projection of the orthogonal to tangent space are linearly independent, and then we try to make the degrees as small as possible. Yeah, so since this is a degrees, so this can be called so-called dimension. Yeah. So here it turns out it's so related to this dimension in the particular point. And it is interesting that we know that for this type of process, Brownian motions on Carnot group, this number can be anything greater than m. So me can be any number greater than m. So in this case, since m equal to 2, greater than equal than 2. So this is any number greater than equal than 2. So this is any number greater than equal than 1. It is anything is possible here. So any combination of numbers here is possible. So any situation is possible. And the final case is m equals 3, n equal 2. In this case, the condition is as follows. We need, if we can find such points, so that we, well, basically we have to find 3 vector fields of degree 1. And if the corresponding action on F are linearly independent, then we have intersections. So I want to comment this result in light of what I said earlier, that, for example, if we have 3-dimensional usual Brownian motions, then they have intersection, and clearly the condition holds here because all vector fields have degree 1. Yeah, but if we take Brownian, if we take processes which are hyperelliptic in 3-dimensional case, so for example, Brownian motion on Heisenberg group, then this condition, if we take 2 processes that are supposed functions are this just x, yeah, and suppose these 2 processes that I consider are Brownian motion on Heisenberg group, which have same distributions, basically the same processes, right? So it turns out this condition doesn't hold. So because at each point we have two directions only, and these 2 directions are same for both processes. So we cannot find 3 different vector fields such of degree 1 such that they are linearly independent, because everything is in one 2-dimensional space. So we cannot find 3. So it is consistent with the known results about intersections of intersections. And note that if we have 2 different processes, which are, if at least in some point this 2-dimensional space in which we can move is different, at least in one point, then that means that these processes have intersections. So this is these 4 theorems actually are for all cases, so we covered all the cases. And we know in each case what is the condition for this to happen, or this. Unfortunately, again, I only can do it on the set view 0. So now, how much time do we have? Sorry, how much?
You have some time.
Yeah,
but not much.
Okay, so what I want to say is that there is a so-called, I will call it condition lambda, I don't know how to call it, but basically it is a condition that is equivalent to all these conditions in this particular cases. So this is like a general condition that can be used for also as necessary and sufficient condition. So here, this condition lambda holds if and only if all these conditions that I previously told you in different theorems hold. And in fact, so the theorem that I need to prove is that if the condition lambda holds, at least at some point, then this holds. So this is another way to formulate this condition. It is interesting because when this condition first appeared, I didn't expect it to be necessary and sufficient. I just thought that it's a nice condition for for me to use in this particular case, but it turns out that it probably is necessary insufficient, well, at least for this. Yes, so I will not give you many details because I do not have too much time, but basically it's a condition that is related to the ability to choose some kind of set of vector fields that have degrees that satisfy some inequality. And if I tell what this condition comes from, it's actually comes from some integral. So remember, I told you that for Lévy process we have a condition in the form of integral. So here, this condition is actually I cannot say that it is equivalent to some integral being finite, but if this condition holds, then some integral with potentials are finite. So this is related to the integral of potentials. Course. Yeah, so now in order to prove this result, I first need to use my previous results about local time. So if we have such local time approximations, then it was proved that this is, by the way, where this condition lambda first appeared in this theorem in 2019, and only later I realized that actually this is a very good condition. So, but so if this condition holds, then we can have this local time, and consequently we have intersections. So it is in this direction the proof is relatively easy because I already have this theorem. And to prove it in the different direction, I need this theorem. So I need in this theorem, I need some measure such that on the Borel set it satisfies this condition, and then this Borel set is not visited by the joint trajectory. Yes. Unfortunately, here I need that condition delta less than 0, but in reality, if we apply condition lambda, then we can only obtain delta equal to 0 in some cases. So we will need some additional statement, and this statement is that the number of points in this set cannot be finite but not 0. So this has probability 0, so this is corresponding theorem. I have to assume that probability space is complete, and then basically if this trajectory visits a set, that means that, I'm sorry, the important part is cut off. So I'm sorry. So if this trajectory visits this set, it means that xn, trajectory with xn, visits this set. So it is this problem of visiting of set by joint trajectory can be rephrased like visiting of one. And this is why we can claim that the set cannot be finite and non-empty, because this cannot happen for one process. And finally, in order to prove, this is the last theorem, and this is a kind of a main new result, because this is what was needed before. In order to complete all this, I needed to prove some kind of estimate for the measure of poles, and here you can see that if we have this estimate, then we can apply the theorem before and obtain the general result. So this is it, I think. Yes, thank you very much.
Thank you. We have a little time for questions, please. Okay, so if there are no questions, then we can switch to the next talk by Marie-Christine Bormann.
Yes, thank you.
Hi, Marie.
Hi, I will share my slides. Just one second.
Yeah, so the topic of the talk, some recent results on Brownian motion with sticky reflection, reflecting boundary diffusion. Please.
Okay, yes. So thank you very much. As you can see from the title, I plan to give a brief overview on some results and also some open questions concerning Brownian motion with sticky reflecting boundary diffusion. And this will mainly be concerning results on functional inequalities and also concerning the associated Fokker-Planck equation. Okay, first of all, I should, of course, tell you what is the setting here and what is this object that I'm discussing. And for that, I should thank Andrei Pilipenko, because he already talked a lot about possible boundary behavior we could consider for Brownian motions. Now for this talk, the setting will be, we let omega be a smooth and compact connected Riemannian manifold of dimension larger or equal than 2 with a smooth and connected boundary. And then we consider the process called Brownian motion with sticky reflecting boundary diffusion. And I would like to characterize that here for you in terms of its Feller generator. So that's the L that is written here. And this L is supposed to be understood as an operator which is defined in a different way on two different parts of the domain. So on the one hand here we have on the interior of the manifold the full Laplacian, which corresponds to Brownian motion in the interior of the manifold. And on the other hand we have a boundary Laplacian here, which corresponds to Brownian motion tangential to the boundary, so along the boundary. And we have a derivative in the outward pointing normal direction with a minus sign. So here this corresponds to reflection from the boundary back into the interior. And I haven't shown you some specific boundary condition yet, because that is a bit hidden here. Namely, we have this condition that LF is supposed to be continuous, so in particular continuous at the boundary, and that's where we get a boundary condition which combines these two parts here. Okay, also I should say this process is sticky in the sense that it has a positive occupation time at the boundary, and we've heard about sticky boundary behavior before today. Okay, also I should say we have two parameters here, this delta larger or equal than 0, which describes how fast is this diffusion along the boundary. In particular, if delta is 0, then we do not have boundary diffusion, just sticky reflection. And we have this parameter beta, which is supposed to be positive and tells us how strong is the reflection from the boundary back into the interior. Okay, we need two more things. Firstly, a symmetric measure, and that will be what's defined here as lambda alpha, which is a convex combination of the normalized volume measure on omega and the normalized Hausdorff measure on the boundary. So alpha here is a parameter between 0 and 1, which is defined like this for a given value of beta. So it's just convenient to write this lambda alpha as a convex combination in terms of this parameter alpha. And then we have the corresponding Dirichlet form E, which is written down here. And again, it consists of two parts. On the one hand, we have an energy term for the interior, and then we have delta times the second term, which describes energy on the boundary. So here we have the tangential gradient, and we integrate only over the boundary. Okay, so that is the object, and coming back again, we've heard already about sticky reflection. So what's new here is this boundary diffusion. Of course, Andrei's talk was in one dimension, so then boundary diffusion does not really make sense, but in our setting, of course, it does. Okay, now, as I said in the beginning, I want to, so the first part, I want to talk about some functional inequalities for Brownian motion with sticky reflecting boundary diffusion. And there are basically 5 works that I should mention here. The first one is by Vitaly Konorovsky, Viktor Marx, and Max von Renesse about spectral gap estimates. And for me, this was sort of the starting point because these next 3 papers are part of my PhD thesis. They contain joint work with Max von Renesse and Fengyu Wang, and they concern Poincare, logarithmic Sobolev, and some Cheeger type inequalities, again for Brownian motion with sticky reflecting boundary diffusion. And then I should also mention there's a very recent contribution by Fengyu Wang on super and weak Poincare inequalities in this setting. Okay, so let's talk about these. And for that, as I just mentioned, we discussed different versions of Poincare inequalities here. And let's talk about these at first. So what's written here in the first line is regular Poincare inequality. So we want to bound the variance with respect to our invariant measure from above in terms of the Dirichlet form. So this is known to give us existence of a spectral gap and exponential decay of variance along our semigroup, or also equivalently exponential convergence to equilibrium in L2. And then there are these 2 other versions of Poincare inequality, namely super and weak Poincare inequality. Both of them are actually families of inequalities. So for the super Poincare inequality, we need a function b going from 0 infinity to 1 infinity. And here we want to take f squared integrated with respect to our invariant measure and want to bound that from above in terms of 2 parts, in terms of the Dirichlet form and in terms of the integral of the absolute value of f with respect to our invariant measure squared. And this is supposed to hold for all positive r, so that's why I said it's a family of inequalities. And then we also have a weak Poincare inequality where we need function a from 0 infinity to 0 infinity. And both of them are supposed to be decreasing. And for the weak Poincare inequality, we want to bound this left-hand side in terms of our Dirichlet form and in terms of the L infinity norm squared. Okay, where here we assume that f has mean value 0 actually. So both of these are versions of the classical or of the regular Poincare inequality and provide different information. So for example, this weak Poincare inequality is weaker than the regular one, and it only provides a sub-exponential convergence to equilibrium. And now in the following slides, I will tell you about results on these Poincare type inequalities for our Brownian motion with sticky reflecting boundary diffusion. And all of these sort of fit into the same scheme because they all use 2 things. Firstly, because we have Brownian motion in the interior and Brownian motion on the boundary, along the boundary of our manifold, we use sort of separate information on Brownian motion in the interior and on Brownian motion on the boundary. What I mean by that is we could consider just simple reflected Brownian motion on omega, so corresponding to the Neumann Laplacian as a generator. And then we could discuss all of these Poincare inequalities. And I denote the corresponding constants and functions by a little omega in the index here. Or we could consider Brownian motion on the boundary, where we just consider the boundary as a manifold without boundary on its own, corresponding to the Laplacian as generator. And I denote the corresponding constants and functions for Poincare inequalities in this setting on the boundary by this subindex d omega. So as I said, these 2 sort of more classical cases provide, in a way, information separately on Brownian motion in the interior or on the boundary. And then for our setting of Brownian motion with sticky reflecting boundary diffusion, we additionally need a way to somehow bring together the boundary and the interior. So we need what I call boundary interior inequalities here. For example, for the regular Poincare inequality, it will be helpful if we can also bound the variance on the boundary from above by the energy in the interior. Okay, now let's go through a few results, and actually I will not do that chronologically, but rather according to how explicit the results are. So first of all, there's this theorem by Wang, where he establishes super and weak Poincare inequalities for Brownian motion with sticky reflecting boundary diffusion. And actually, he makes a distinction between the case where delta is larger than 0, so we do have boundary diffusion, and the case where delta is 0, so we don't have boundary diffusion. This latter one is usually the more difficult one. And first of all, he shows that a super Poincare inequality is fulfilled and gives an upper bound for this E function in terms of these two parameters. And as I said, these two standard cases providing separate information on interior and boundary. And then he makes the following assumption in order to show further results. Namely, he assumes that there are some nice auxiliary functions, G and H, sufficiently regular and such that their normal derivative on the boundary is equal to 1, and such that we can control their gradient and negative part of the Laplacian in L2 and in L infinity. And if that is fulfilled, then he shows that also weak Poincare inequality is fulfilled with a given upper bound. And we can also then treat the case where there's no boundary diffusion, just sticky reflection. We can show that there's super Poincare inequality and weak Poincare inequality, and give upper bounds for these rate functions A and B. However, all of them feature, on the one hand, separate information on boundary and interior, but also they also feature these auxiliary functions, which we do not know explicitly in his theorem, but we just assume that they do exist. So in that way, the upper bounds that he gives are not quite explicit. But instead we have following two results. So the first one is due to Vitaly Konorovsky, Viktor Marx, and Max von Anesse, and they showed that if we have a positive lower bound on the curvature and positive lower bound on the second fundamental form on the boundary, so we have a convex boundary, then a regular Poincare inequality holds with an explicit upper bound for the Poincare constant in terms of these parameters, curvature bounds, and again, these standard Poincare constants. Okay, so this is treating a regular Poincare inequality. It is nice because in a way it's more explicit. It is also nice because here they only assume lower bounds on the Ricci curvature. There are no upper bounds on the curvature, which makes sense because more like higher curvature should intuitively only help us when it comes to convergence to equilibrium. What is not so nice about this is that it only allows to consider cases with positive curvature and convex boundary. And instead we have this second result due to Max von Anesse, Feng Wang, and myself, where now we assume we assume lower and upper bounds on Ricci and sectional curvature and on the second fundamental form on the boundary. And then again, we can show that a Poincare inequality holds under this assumption, and we can give an explicit upper bound, which now also involves these upper curvature bounds. So as I said, that this assumption is not so natural. However, what's nicer about this result is that it allows to consider cases with negative curvature and non-convex boundary as well. I should also say that what is in the background of this theorem is again such auxiliary functions of the form of G and H here. However, instead of leaving this assumption just as it is stated here, we make these curvature assumptions and give an explicit or explicitly constructs such auxiliary functions. So that's why this result in the end is more explicit in terms of these curvature bounds that are assumed. And in the same context, I should also mention that there's also a logarithmic Sobolev inequality. So as a reminder, we say that a log-Sob inequality is fulfilled if we can bound the entropy with respect to our invariant measure of f squared from above in terms of our Dirichlet form, which is nice because it gives us exponential decay of the entropy along our semigroup, or also hypercontractivity properties for the semigroup. And again, one could firstly consider separately the case of reflected Brownian motion on omega or just Brownian motion on the boundary. So that's the log-Sob constants d omega and d omega then. And similar to the previous result, we can show that if we're in dimension larger or equal than 3, if we have the same curvature bounds as before, then the logarithmic Sobolev inequality holds, and we can give again an upper bound, which now gets quite complicated, but just features these parameters and curvature bounds, dimension, and separate information on what is going on in interior and on the boundary. Okay. So all results that I mentioned so far, if they were explicit, then they were explicit in terms of given curvature bounds. Instead, there's another type of results, namely so-called Jigger type inequalities. And for that, let's look at an example to easily define some notation here. So we could consider, for a simple example, just a unit ball in R3 for our manifold omega. And then we could cut that in half horizontally, and we could call the lower half A. And then A has a boundary, and part of the boundary of A lies in the interior of omega. So that's the surface where we cut it, what is drawn in red here. We call that the interior boundary, the I of A. But also part of the boundary of A lies on the boundary of omega. That's this entire southern hemisphere here, and we call that the exterior boundary of A. And this, as a subset of the full sphere, again has a boundary which is just the equator, and we call that DE of A. Okay, and now one can define some Jigger type constants. So classically, the Jigger constant HC is defined by taking an infimum over subsets A of our manifold omega with some restriction. For example, their exterior boundary cannot be too large. It must have the size of the full boundary. And then we want to minimize this quotient of the size of the interior boundary of A and the full volume of A. So that's more or less the classical Jigger constant, and then we can define versions of this which also incorporate the exterior boundary of A or this DE of A. And then we can also alternatively give upper bounds for our Poincare constants in terms of these Jigger type constants as opposed to in terms of some curvature bounds. So that's what's stated in the theorem here, both for the case where we have no boundary diffusion, so delta equal to 0, and for the case where we do have boundary diffusion, we can give upper bounds on our Poincare constant in terms of these Jigger type constants. So we have HC and HB for the case without boundary diffusion, and with boundary diffusion, we also use this HE here. Now this sort of result in theory is nice because these inequalities are pretty simple, and it seems like we can capture enough of the geometry of the manifold in terms of these 2 or 3 Jigger type constants. In practice, what's not so nice is that for a given example, it's not always easy to compute these Jigger constants explicitly. Now, I should state that everything I've told you so far It would also work if I would add a drift to the Brownian motion in the interior and a drift to the Brownian motion on the boundary. However, there are instead some other aspects and questions that have not yet been established and discussed. So for one, I was just talking about a Cheeger inequality, which gave us an upper bound on the Poincare constant. And if there is such a Cheeger inequality, then the next question is whether there is also what one calls a Buzard type inequality, which would mean that we could also bound our Poincare constant from below in terms of these Cheeger constants. So that is something that has not fully been established yet. Also, in general, all the results that I showed you were on upper bounds for Poincare and log-sub constants. So there's, in general, there are barely any results on lower bounds for these constants. And one more aspect I should mention is that all the results I talked about so far, they are proven via analytic methods. And instead, if we look at, for example, just simple reflected Brownian motion, then it is known that when one can also obtain good results in terms of some coupling methods or more stochastic methods. That's also something that has not yet been done for Brownian motion with sticky reflecting boundary diffusion. And one more thing that I should mention is I've only considered one particle following Brownian motion with sticky reflecting boundary diffusion now. Instead, one could also consider a system of interacting particles where particles can come together, stick together, diffuse together, and then separate again. So that would be also a further generalization to show functional inequalities in that setting for such an interacting particle system. Okay, so that was the first part of the talk. And now, as I mentioned, I also want to talk a bit about the Fokker-Planck equation associated to this Brownian motion with sticky reflecting boundary diffusion. So I wrote here first the generator again. Now for simplicity, the parameter beta that was here before is set to 1. And now we are interested in the Fokker-Planck equation. So we want to describe the time evolution of the probability density function of a particle. And our Fokker-Planck equation is dt rho is equal to the adjoint of L applied to rho. And in the following, I will always write probability measures rho as a sum of two parts, one that is on the interior and one that is on the boundary. And I will also always identify measures with their densities. And then we can write out our Fokker-Planck equation in this setting as follows. So we have dt omega is equal to the Laplacian of omega in the interior. Dt gamma is equal to delta times the boundary Laplacian of gamma minus normal derivative of omega. And we want that in a sense of taking traces. The interior part omega and the boundary part omega, they agree at the boundary. And now what people have discussed concerning this Fokker-Planck equation is whether it can be interpreted as a Wasserstein gradient flow. Why would one be interested in that? Well, first of all, there's just theory on existence results and so on for gradient flows. So one could profit from that. And also one can gain some insight, some physical insight from interpreting an equation as a gradient flow equation. And I will now talk about the contributions made in these two works here. But first of all, I should maybe state the obvious on the next slide about gradient flows, metric gradient flows. So if we were in the setting of a smooth Riemannian manifold and we're discussing a gradient flow on a smooth Riemannian manifold, then this can be made sense of completely rigorously. So we have a curve rho of t, and then we can make sense of d rho by dt as an element of the tangent space of our manifold. And on the other hand, we have some driving functional E on our manifold. If it is nice enough, it has a differential, and using the metric tensor on our Riemannian manifold, we can make sense of its gradient, which again is an element of the tangent space. So everything makes sense if we have the structure of a smooth Riemannian manifold. However, if instead we are only on a metric space, then of course we only have metric information and some driving functional, but we have to find a different way to make sense of such a gradient flow equation. And I just mentioned here some different notions of metric gradient flow. I don't want to go into detail. I just want to mention them. So firstly, we have what's called autocalculus, which is not completely rigorous, but instead, even if there is not really the structure of a Riemannian manifold, this autocalculus tries to formally make sense of the notion of tangent vector and gradient and so on, in order to still make sense of a gradient flow equation. So that's not quite rigorous, and instead there are other notions which really only use metric information, such as generalized minimizing movement schemes, which uses a discrete approximation, or for example what's called curves of maximal slope. So as I said, I don't really want to go into detail here. Instead, I just want to briefly talk about 2 or 3 results in this setting. And here we make a distinction between the cases delta larger than 1 of fast boundary diffusion and slow boundary diffusion. So first of all, what was shown in the case where delta is equal to 1 is that we can think of our Fokker-Planck equation as a Wasserstein gradient flow in the following way. And this is rigorous in the sense that this only uses metric information. So we can use the driving functional, that is the entropy, with respect to our invariant measure. And for a metric structure, we just have to use the standard quadratic Wasserstein distance. So that's the case delta equal to 1. And then there's a strong conjecture for the case delta larger than 1, which says that also in this case of fast boundary diffusion, we can think of our Fokker-Planck equation as a Wasserstein gradient flow with the same driving functional, but with a different metric. The metric here is still a Wasserstein metric, but with respect to a different cost. Namely, we define a cost of going from some point x in omega to y in the following way. We take an infimum over length of curves connecting x and y, and the relevant part is over here. So curves are allowed to run through the interior of omega or tangential to the boundary, but they are not allowed to go orthogonal to the boundary. So they are not allowed to leave omega. But interestingly, if delta is large, then this factor 1 over delta is small, of course, which means that it's cheap to go tangential to the boundary. Okay, we define a cost function like this, and the conjecture is that with the Wasserstein metric based on this cost function, we do still have such a gradient flow structure. One can see quite easily that this fails for smaller values of delta, and this is the last theorem I want to talk about, because now for the case of slow boundary diffusion, we have shown that while we can think of our Fokker-Planck equation as a Wasserstein gradient flow in the sense of Otto's calculus, which was this non-rigorous notion, we can show that there cannot be a metric on omega such that our space together with this metric and our invariant measure is still a decent metric measure space, and such that our Fokker-Planck equation can be interpreted as a metric gradient flow with respect to still the same driving functional, but now the metric coming from this D. So what's interesting about this is that for this regime of slow boundary diffusion, we have an example here where different notions of metric gradient flow work or do not work. So namely, autocalculus seems to give a valid interpretation as a gradient flow, but a more rigorous metric notion does not work. Okay, And I think I'm out of time, so I stop here and
Yes.
thank you for your attention.
Thank you for the interesting talk. So now if we have questions, then please.
I have a question. You get a condition on the Ricci curvature, and after this, when this condition is more or less uniform, then you have the desired inequalities. But how it depends on the boundary condition? Does it depend heavily, or it remains the constant remains more or less the same? It doesn't depend on reflection, sticky, or something happens on the boundary.
So you're asking how these, for example, these Poincare constants change with different boundary behavior?
Yes, exactly. How it depends on the boundary condition?
Yes, so it can depend very much on the boundary condition. For example, if we look here again, it can change very much with this parameter delta that is changing. So if we have sticky reflecting boundary diffusion and the boundary diffusion is fast, then that makes the Poincare constant a lot smaller because the process can spread out also via the boundary, which is not possible if you just have reflected Brownian immersion, for example. So the case, speaking non-rigorously, it always gets better if you have more boundary diffusion. It gets worse if you have more stickiness, because somehow a particle would stick to the boundary, so it cannot really spread out easily. So then the Poincare constant gets worse.
Okay, thank you.
If I may add a comment, so we also call this model the ring road model. So the Poincare constant tells you how mixing the process is.
Yes.
If you can use the highway around the center, which is very fast, then the process mixes much better than if you don't have the highway around. So this is how you have to think about it. It's a city which has now a highway, and the highway can be very good for mixing.
I see. Okay.
May also I ask a short question?
Yes, please.
So my question about the last part of your talk about this auto description of sticky reflected behavior. As I understand, also you can talk about that in terms of that the short time asymptotic, and maybe so now having this picture. So you can also state a similar Vardan lemma. Maybe you discussed that in your paper, it seems, but how rigorous that is. So it is only on the heuristical level, or you can indeed so prove the Vardan formula and so on.
So I'm not entirely sure what you mean in this case. So.
I mean, so if you are familiar, for instance, with this paper of Max and Teosturm about Wasserstein diffusion, where they discuss the logarithm of the probability.
Yes, so I'm familiar with Vardan's formula.
Yeah, so here you can have a similar, if you consider, for instance, similar kind of the dynamics and so on, a similar result now can be obtained from that picture.
Well, I mean, I see Max is nodding, but actually, so what we assume for this last part is that such a Vardan formula holds. And we actually show that if we make that assumption, then there is not a rigorous metric gradient flow interpretation.
But not in the inverse way, right?
Not in the inverse way. But I think probably this is not quite the answer to your question, because I think originally you were asking more about the auto calculus perspective, right?
So if I may add one more thing, Marie. So since we are in Dirichlet form situation, basically, if we have the regime of slow boundary diffusion, the Varadhan formula is, because we work with Dirichlet forms and stuff, we have an explicit Varadhan formula, but the metric that comes out of there will always be the same, regardless the parameter. So what this is why in a way large deviations here does not tell you the Otto picture. That's the problem. So this is why the worlds divert. So in regular situations, Varadhan formula and Otto can be related to one another. But here, Varadhan formula exists, but gives you always the same object, regardless the parameter. And that cannot be true if there is still the one-to-one correspondence between Otto and the Varadhan formula. So there is a Varadhan formula, but it's always the same. So in a way, there is a large deviations principle here, which is not precise enough to identify all parameters of the problem. So there is a Varadhan formula, but it's always the same, which is a problem.
Yeah, I see.
Okay,
thank you.
If there are no more questions, then let's go to the next speaker, Katerina Kustareva.
Yes, I'm here.
Okay, so the talk is complexity of compact sets in stochastic flows.
Yes, let me please to share my screen. And yes, thank you for introduction, and let me thank the organizers for the opportunity to participate in the conference. It's a pleasure to present my work here. So I'd like to begin with a reminder of the definition. And this is a notion of a stochastic differential equation with interaction, introduced by Dorogovtsev in 2003. And general form of such equation is following. As you see here, xut represent the trajectory of a single particle that starts at point u in the RD space. Μt is a probability measure that describes the mass distribution of the entire system at a given time t. W dp dt is a random measure describing randomness across space and time, and probability measure equipped with Wasserstein distance. Next, let me highlight some special features of stochastic differential equation with interaction. First, the dynamics depend explicitly on the system mass distribution, and unlike standard SDs, where a particle evolves under local driven diffusion, here the measure μt represent the entire configuration of the system at time t, and each particle's path is influenced by this global distribution. And solution to SDs with interaction must be considered in infinite dimensional space, such as the space of measure of OR functions. So, and here some key difference from standard SD. So standard SDs describe the evolution of one particle, while SDs with interaction must account for the interaction between particles, making their motion interdependent. And SD with interaction involve an entire flow of particles and their evolving mass distribution. And the third one, in general, for an SD with interaction, xut t greater equals 0 for fixed u is not Markovian. To illustrate the concept, let me show a simple example of an interacting particle system with a noise. Here we consider n particles with the dynamics, where x bar t is empirical mean of all particles. So the drift term pulls each particles toward the mean, modeling attraction, and the diffusion term represents a common noise affecting all particles simultaneously. And I'd like to show you some simulation, and my simulation is set up as follows. We need time horizon, step size. I took 10 particles. So initial position uniformly drawn, I mean initial positions uniformly distributed in -20 to 20, and noise term is identical across all particles. So here we see the trajectories of 10 particles simulated according to the previous system. And again, all particles start from widely separated position in the interval. And because of the attractive interaction toward the mean and the presence of the same noise term, the trajectories gradually approach one another. And the result is synchronization. The system evolves so that particles move together despite starting far apart. So the motivation. We start with a compact set K0. And under the interacting flow, we define KT, meaning that the flow maps the initial set K0 to a new set KT at time t. And our goal is to study the properties of KT. In particular, we want to understand how geometric and complexity-related characteristics of compact sets behave under such flows. And to study these sets, we leave them into a Gilbert space. So let H be a separable Gilbert space, and let H small be a continuous differentiable embedding. And for compact set KT, we define its lifted image, 18. And the properties of KT are then reflected in the geometry of AT inside the Hilbert space. And this lifting is very natural in machine learning. For example, in kernel methods, we define a feature map. I think I can write, for example, phi from RD to HK into a reproducing kernel Gilbert space, such that x, v, y, hk equals chi x, y, where k is a kernel function such as, for example, Gaussian RBF kernels are popular. And this allows linear separation in HK of data that is not linearly separable in RD. And for example, well-known neural networks implement some similar embeddings, two-layer network. So simple model with some activation sigma, and the mapping can be, let's suppose, hx can be, for example, some weights sigma. Activation function, again, weights plus bias plus beta. And here, h of x is a nonlinear embedding on the input into a higher dimensional feature space. And the distance and inner product in this feature space encode semantic similarity between data points. And our approach follows the same principle. Once KT is mapped into a Hilbert space, we can study its geometry using linear and spectral tools such as entropy and effective dimension. So again, once we lift a compact set into a Gilbert space, and we can introduce quantitative measure of their complexity. And today we will focus on three notions. First, quadratic entropy introduced by Andrei Anatolyevich Dorogovtsev in 2010, defined using orthogonal projections. Then Kolmogorov entropy based on covering numbers, and effective dimension. And with these definitions, we now have opportunity to discuss metric properties of compact sets, some another properties, and their asymptotic behavior under interaction flows. Let's start with quadratic entropy. Let A be a non-empty subset of a Gilbert space, and the quadratic entropy of A is supremum some norm PUN, where PUN is an orthogonal projection of UN onto the orthogonal complement of the span of all other vectors. So UK is not equals n. And this definition measures how much of each vector UN is new compared to the rest of the family. Let me now give an example where quadratic entropy can be estimated. So we consider n independent Brownian motions in Rd with d greater or equal to 3, and take a compact set K, fix epsilon greater than 0, and we define the embedding here, where bu epsilon is the ball of radius epsilon around u. And in this embedding, the scalar product here is the lambda d, where is Lebesgue measure, and then we can obtain the estimation where k epsilon is epsilon fatting of k. And with this in mind, we define the covered volume functional r epsilon t, and then we have equations. So what is asymptotic when t goes to infinity? Continuing with this example, we take this result. For fixed n, dimensions d greater than 3 and radius epsilon greater than 0, we have this relation, where again CD is the volume of unit ball in Rd. And this means that over large time horizons, the average covered volume grows linearly in T. And the coefficient depend only on the number of Brownian particles, the dimension, and the volume of epsilon ball. Let us now consider another example based on Einstein-Uhlenbeck dynamics. We take initial positions xi0 that are independent and normally distributed, and the dynamics are given by the formula. Each coordinate evolves as a mean reverting process, pulled back toward 0 with the strength alpha, while being perturbated by independent Brownian motions. And as before, we define the average covered volume functional. For the Einstein-Uhlenbeck system, we obtain the following relation, again for fixed epsilon greater than 0, where again CD is volume of the unit ball in Rd. We have here the term theta m. The probability is that m independent Einstein-Uhlenbeck particles are initially located within distance to epsilon of each other. And how it is obtained just using the inclusion-exclusion formula applied to the union of poles. And after averaging over time and using the stationarity of the Einstein-Uhlenbeck process, the contribution of each m-fold intersection becomes a constant depending only on theta m. Let's now return to the general case of stochastic differential equation with interaction. And here we will use the result due to Dorogovtsev and Karlikova 2005. Assume the drift had the form here with a Lipschitz kernel phi satisfying the monotonicity condition. Under the condition, the family mu t is shift compact and trajectories contract. So interacting flows with monotone drift exhibit asymptotic synchronization of trajectories. And this is large time behavior we will use to study the geometry of transport compacts. So based on this contraction property, we can describe the asymptotic for this case. So suppose the interacting flow satisfy that for any finite set of initial points, u1, um, the distance vanish. And then the following holds: the intersection of the corresponding balls converge to the volume of a single ball. Moreover, if we average over time, we obtain this result. And this means that asymptotically the system behaves as if all trajectories collapse to a single point, and the only geometric scale that remains is the ball of radius epsilon. To analyze compact sets in Gilbert space, we also need another characteristics, and I want to give a definition. First, the support function for a set A, which is a subset of H, and the unit vector E. We got this function, which is describes the maximal extent of the set in a given direction. And the second one, the concept of a sigma square bounded set following Sudakov and Rogovtsev. Again, we have a subset and and is called sigma square bounded if the following inequality, the following bounds hold, and where the supremum is over all orthonormal bases in H and in Gilbert space. And the Rogovtsev introduced such sets in connection with the notion of quadratic entropy, and these sets are also well suited for studying the behavior of the Gaussian is-normal process on them, which is important for entropy bounds. So another example, and next notion is Kolmogorov entropy. Here we have an A epsilon. In the maximal number of sigma balls needed to cover A. So, and then we just took ln. And if the set is just, let me go through the example one by one. If the set is just the interval from 0 to 1 on the real line, then we need about 1 divided by epsilon intervals of length epsilon to cover it. So in this case, we have this result. And if the set is the unit cube in RD, there's a collection of all points with coordinates between 0 and 1. Then the number of covering balls is about 1 divided epsilon power d. So here we have this result. And finally, if this set is finite with m points, then for small epsilon, every point needs just 1 ball. So this example shows the range from logarithmic growth for the interval to dimension times logarithm for the cube, and we have a constant for a finite set. The third notion we use is the effective dimension of a compact set. Again, let a subset of H be compact, and let mu be probability measure on A. And we define the operator as mu. And since A is compact, the operator is nuclear and it has eigenvalues lambda I. And then we use normalized spectrum divided by trace of S mu. And then the effective dimension with respect to mu is defined as follows. Intuitively, this is the exponential of the Shannon entropy of the normalized spectrum rho I, It measures how many directions effectively contribute to the geometry of I. So let me illustrate this definition with two classical examples. First is a sphere. Take the unit sphere in Rm, and if we put the uniform measure on the sphere, then by rotational invariance, the operator is proportional to the identity. And this means that all eigenvalues are equal to 1 divided by m, and then the normalized spectrum is also 1 divided by m. And as a result, we complete dm equals m. And second, the ball, take the unit ball in Rm with, again, with uniform measure. By isotropy of the ball, the operator is again proportional to the identity, and the eigenvalues normalize in the same way, given again rho I equals 1 divided by m. And as a result, again, we took this mu, m. And so, yes, it turned out that we can bring together two different entropy notations and obtain an estimate. If A is sigma squared bounded, and then there exists a constant, positive constant, such that we take this bound. Here, H2A is quadratic entropy, while this Kolmogorov entropy, and a epsilon is the covering number, which we use. So we see that these two approaches, one based on orthogonal projections and the other based on metric coverings, can be connected. And the quadratic entropy of A is controlled by Kolmogorov entropy through the covering interval. And now I want to prove this result. So we use some hint. We will use a Gaussian width. And so let G be a standard Gaussian in H. And we define the isonormal process Gx, which is equals inner product of J and X. And we define the Gaussian width. It's expectation of the supremum of Gx over A, and our goal to understand actually A is correct. And yes, again, I recall the definition of the Rogovtsev entropy. So the sum of squared lengths of the parts of UK are orthogonal to the other vectors. And then we can use Grommer-Schmidt residuals. We defined VK, the orthogonal residuals of UK after removing components along V1 and so on, VK minus 1. And then each UK is the sum of the first car residuals, and the residuals are mutually orthogonal. And then we compare projection with residuals, and projections all onto a large orthogonal component cannot increase the norm. So hence we get this result. And then we can build a Gaussian martingale. So we define a partial sum. We define a partial sum here. So sum of Gaussian coordinates along Vj, and orthogonality of Vj gives independent increments. Sk minus sk minus 1 equals gvk. So with this variance. And thus we have the expectation, and quadratic variation equals the sum of squared residual norms. Also, since U is the sum of Vj, GUK equals SK, and yes, from this we will get this result. So we converted the projection sum to the quadratic variation of a Gaussian martingale tied to max escape. Then we already reduces H to A to a sum of squared norm of residuals Vk and link these residuals to a Gaussian martingale. So now I use the Boch-Golder-Davis-Gandhi inequality, gives a two-side estimate for Gaussian martingale in our case, we can see it. The expectation of the maximum of the martingale scale is equivalent to the square root of the sum of squared norm Vj. And from the left inequality, we obtain this one. And then we replace sk with uk. And as we have this result, so we can rewrite the bound. Okay, maybe we'll write it. Okay, we can write. We can rewrite the bound as we will get this part. And for a finite set, the maximum over our GUK module GUK can be bounded by the supremum. And since taking both u and minus u at most doubles the supremum, and we get to suit. So, and putting these pieces together and taking the supremum over all finite subset u, we obtain this result. So quadratic entropy is bounded by a constant multiplied the square Gaussian width. We now bound Gaussian width by covering numbers via Dudley's inequality. And this is links VA to Gaussian width to Kolmogorov entropy. So we defined on A, we define metric on A by the xu equals norm x minus u, norm distance in H, and let the diameter, it will be largest distance in A. So for epsilon greater than 0, let n a epsilon be the minimal number of radius epsilon ball covering R A, and we take Dudley's inequality, and so there exists a constant CD greater than 0 such that Gaussian width is at almost a constant times the integral from 0 to diameter of the square root of log covering numbers. So, and then on the previous slides, we proved two facts. And to combine these bounds, we substitute in the second inequality in the first case. And if we denote the constant equals C0 CD squared, then the final form of the inequality is here. And this completes the proof of the theorem, which I announced earlier, and quadratic entropy can be controlled entirely through Kolmogorov entropy. Now I want to present as a corollary of the entropy inequality, obtain some bounds for the effective dimension. Let a probability measure mu be supported on A, and we define the operator, and it has eigenvalues lambda I, and we normalize them again. And using this normalized spectrum, we define this, we can call the Shannon entropy, and then it's just entropy for the particular mu. And with this definition, we obtain the inequality. These inequalities mean that the mu A lies between the ratio of the trace to the largest eigenvalue and the rank of the operator. And moreover, if the set A is sigma square bounded, then we have the stronger lower bound. Okay. And I want to present some result, how we can estimate entropy when the eigenvalue spectrum decays geometrically. So we define the normalized eigenvalue, as you can see. This is a geometric sequences depending on the parameter beta, and the entropy of the spectrum is given by, again, I will write this formula, the minus sum of I beta ln. So it is this one. And carrying out the computation, we can obtain du mu I, and then can see the asymptotics. So we put Q equals epsilon in the power minus B, and as B goes to 0, the spectrum is almost flat. Entropy behaves like minus ln plus 1, and the dimension grows as exponent divided by beta goes to infinity, and as beta goes to infinity, the spectrum concentrated on the first coordinate, so entropy vanish, and then we can see this result. So for today, that's all, and here are my references. And thank you so much for your attention.
Okay, thank you for the interesting talk. So it's time to ask questions. Please.
I have one question, if I may.
Please.
I have a question. So you mentioned the application to machine learning. So which of these entropy notions or complexity notions would be mostly appropriate if you want to say that a certain measure or a certain set can be represented nicely by a small neural network or so? So can you connect this, if you wish, the size or the complexity of a set, if you identify it, if you wish, with the corresponding uniform distribution on this set, can you identify it somehow with the complexity you need in terms of a neural network to represent that? Is there any connection?
Yes, of course. I'm trying to implement the Rogovtsev entropy in well-known algorithm as a term of regularization, and I have some result. And then I'm trying to calculate the effective dimensional in like using the small grid, just in a Karpet-Sierpinski or you know, some another figure. And yes, I do it basically not so bad. And of course, in machine learning, effective dimension is the most appropriate. Why? Because it's directly reflect the capacity of a neural network representation. Example, since it measures the number of dominant direction and the spectrum of the operator. So, and the quadratic or Kolmogorov entropy quantify complexity, but effective dimension is the best representation for generalization.
I see. Is that already written in some paper of yours, or is it still some work that is in progress?
In progress.
I see. I will be very interested to see that. Thank you very much.
Thank you.
Okay, thank you. Do we have other questions? Okay, if no, then let's skip to the next speaker, Kirilo Kuchinsky.
Hello, everyone.
The talk about logarithmic Sobolev inequality for stochastic differential equations with interaction. Please.
Okay. Do you see my screen?
Yes.
Okay. My microphone works.
Yes. Yes.
Okay. Yes. It's honor to be here. Thank you for all organizers. And I understand that we're a little bit beyond the schedule, so I'm not try not to take all the time.
No, but you is the last speaker, so.
Okay, yes. First of all, I would like to start with logarithmic subelif inequality. It was already mentioned here today. And if we have probability measure, and we say that it satisfies logarithmic subelif inequality with some positive constant, if any function IH, this holds true. And actually, it was firstly introduced by Leonard Gross in 1975, and he finds a constant C for in the Gaussian case. Okay, and further is stochastic differential equation with interaction. The previous speaker already mentioned it, so I briefly say that it was introduced by Andrei Anatolyevich Drogovtsev, and the main idea of it is to incorporate interactions, one particle which starts from point U, and by adding some measure mu t, which is a push forward measure of mu0 by mapping X. And it's I want to mention that it's a random measure, and it will be important in further of my talk. And okay, so when I mentioned that it incorporates interaction, we can actually consider some explicit function, for example, b, and define it using some potential phi. And the idea is for point xut, we go over all points v, and because mt is push forward measure, we can actually replace with measure mu0, but v will be replaced with x yt. And the idea that the point xut, it's interact with all other points by measure mu0. Okay, and for example, we can take phi like some identity function, and in this case, it's just distance to the center of mass at time t. Okay, and further in the my talk, I assume that there is some constant L such that function phi is bounded by such inequality, and if is bounded, then we can actually easily prove that this function b itself is also has the same bound, and we just put explicitly read what is bx1, bx2, then we take one integral sign, and we can using the assumption, this one, yes, we got this inequality, and just integrating over the whole measure, it's just one, and we from inequality on this potential, we get the inequality for the whole drift term. Okay, and as I mentioned, stochastic differential equation with interaction, they considered the random measure, and it's a little bit complicated. So for start, we want to consider some simple example. For example, just a deterministic case R1, and consider this the same drift term, the same function b, the same function phi, and just ordinary differential equation. And we consider that our measure mu0, it satisfies logarithmic subelif inequality with some constant c. And in this case, it's we can actually try to calculate it explicitly. And yes, and using the definition of mu t as a push forward of mu0, we can actually mt, we can swap with mu0 by replacing x with y2. And using this, we actually entropy for F and G, they are the same, just change variable. And in the case of when Gx is given like this, and then we for Gx we can use if we can find actual derivative according to with respect to x, and yes, and just the model of G derivative of G squared is just the product of this square root of these two guys, and now we can actually using logarithmic Sobolev inequality for mu0, which we assumed, and then we can explicitly just using change variable read it how it looks, and using again change variable in the other side, we can we can rewrite it again. So in the left hand side and right hand side, we in both cases we have mu t. And if we want to get the upper bound for logarithmic Sobolev inequality for mu t, we would like to have some universal constant lambda, capital lambda t, which is bound for such derivative. And in this case, it's actually constant looks like that, and how it can be calculated if we replace it, if we define some function j, which is derivative to the with respect to the initial position, and we take a derivative over time. This j in point 0, its derivative is actually 1, and we can find explicit solution for this function j. And because it was mentioned that our function phi has some bound, then actually this function has the same bound L, and we can actually find the explicit bound for modulus of J. And in this case, in the one-dimensional case, using like simple interaction term, we can find that the constant in the case of logarithmic Sobolev inequality, it can be calculated explicitly. And okay, this was a simplified deterministic case. What is the next step? We would like to add some randomness to our system. And the idea is considered SDE, but we would like to add a diffusion term, just some sigma constant with Brownian motion. And now our coefficient depends not on mu t, which was push forward of push forward of our solution xt, but we consider it as just low. And this is actually this equation is Makin-Vlasov equation, and the idea why it's simpler than case than in general stochastic differential equation with interaction, because this measure is deterministic. It's the first one, and the second one is that we actually have a Markovian structure, because we can actually use semi-group techniques, and using semi-group, we can and using the Bakery-Amirou theory. In this case, we can actually explicitly again calculate what is logarithmic Sobolev inequality in this case looks like. And for example, it's I took it from I found it in the Manmar, Sharan, and Wong in 2024, and it states that if exists some time t and some constant L, such that and this condition is identical to the ones that we want to consider in stochastic differential equation with interactions. And if our initial distribution satisfy logarithmic Sobolev inequality with some constant C0, then we can find explicit form of constant Ct for mu t. Mu t, it's just the law. And as I mentioned before, it heavily relies on the Baker-Emery criteria, and it's actually the main tool which is used is the semi-group. Yes, actually, it's all I wanted to present here today. So, and yes, it's all.
Okay, so this is all, yes?
Yes, this is all.
Okay, so now it's time to ask questions. So, are there any questions, please?
I have a question. I mean, obviously, there is a possibility to connect this somehow with generative models. Did you think about that? That there is
Generative models like AI diffusions?
Yeah, exactly. So
unfortunately, you speak about just Makin-Vlasov or stochastic differential equation with interactions?
no, I mean the latter. I mean the stochastic differential equations with interaction. I mean, of course, this is a little bit probably very speculation now at this moment, but so well, basically you want to construct a map or even a flow that connects two measures, and if in your interaction, right? So you could consider the current distribution, and you could somehow include in your interaction. You could be more complicated and have something like a distance of your current distribution towards a target distribution, something like this. So suppose you. So I'm doing a little bit of a speculation at the moment. So sorry for this. It's probably not correct.
It's fine.
But I hope, I mean, okay, so you introduced or you presented a very simple kind of interaction, right? So where you basically have self-interaction through this potential B or F, as you call it. Okay, here B, you call it. Okay, but now suppose you introduce another term in the interaction, namely somehow you measure somehow the gradient of the Wasserstein distance of your current distribution to a target distribution. Do you understand what I have in mind?
Yes. For example, mu0 is like some distribution of Latin space, and then we want to generate some image.
Exactly. And suppose you have some terminal distribution, which you call mu, and somehow you introduce a drift which basically pushes you towards this terminal distribution. I mean, that would be an interesting, I mean, of course, it's not directly connected to what you said, but it would be very interesting to study if we can use any kind of regularity or so.
The only problem that I see is if we have mu0, it's just distribution, but MT it will be random distribution.
Correct.
It's a little bit hard to how to apply it in the specific case, for example, for generation images. So,
well, I mean, you could even think of okay, it's correct. So the map that you would construct here is not a deterministic map, right?
Yes.
So but it would be some sort of a random map. But why not? I mean, okay, but I'm sorry. So I was just offering this idea that came to my mind. It's not very concrete. It was very abstract. But I think it's very interesting. So this kind of research is very interesting, and I see really again connections to machine learning, which would make it even more interesting. So I'm sorry it was not very structured what I said, but I wanted to offer some reaction.
Totally okay. It's a great question. Thank you.
Thank you.
Okay. Any other questions? Okay, so then if there are no more questions, then I think we can finish the session and thank all the participants for participation.
Yes, we are finishing our program of the conference. Hope that this is second, not last conference, but just the beginning of the long series of annual conferences, Kyiv-Leipzig.
Yeah, so thank you also from my side. I think that was very nice, and I hope it will have continuation. And I was very pleased about the scientific level. I think it was very interesting talks. I enjoyed it very much. Thank you, Andrei Anatolovich, for doing this together with the Leipzig people, and I think we will have it again. Thank you very much.
Okay, and we encourage all participants to send PDFs of talks so that we can
And not only
show
PDF
them.
of talks, but if you want to
Papers
publish paper, please consider our journal Theory of Stochastic Processes as one of the variants. By the way, from the next week, we are starting our weekly seminar, Malarian Calculus and Applications. Everybody of you will get announcement. Please participate at least to listen talks, maybe do talks, and so on. So thanks everybody, and bye.
Goodbye. Thank you.
Thank
Bye.
you. Bye bye.